Okay, I think we can get started. It's 9 a.m. in California. Good morning, everyone. Good afternoon and good evening, depending on where you are. Welcome to the portable stimulus session. And today we have, three very interesting PSS paper discussing the experience that, the presenter had with portable stimulus. The first paper is the PSS action sequence modeling using machine learning, how machine learning is used to close the curves quicker. And it will be presented by Moonki Jang. Moonki worked at Samsung Electronics, developing mobile SoC. Since 2010, he has been responsible for the test platform development for the Samsung Exynos application processor. Currently, he is in charge of the design verification for CPU subsystem and coherent network in the system LSI business at Samsung. You can start the presentation now. Yeah,
someone who got a bit irritated. This is Frank. Frank changed the RTL for one field in one register, and he didn't tell anybody. That caused the software on the chip to stop working, which caused the drone it was controlling to crash. It's the home of someone who got a bit irritated. We interrupt this commercial to bring you this important message. It has come to our attention that many design teams suffer from non-automatitis or scriptophobia. These have been known to cause headaches and respin regurgitation. If you experience these symptoms, contact Semaphore for a no-obligation checkup. You don't have to suffer. Reach out to Semaphore. We now return.
Hi, nice to meet you. My name is Moonki Jang. I'm working at System LSI division of Samsung Electronics. It's my honor to have opportunity to present at the DVCon again. In this presentation, we will explain how we implement PSS with machine learning for reproducing deadlock condition on the simulation level. Let's start with our motivation of this study. Most of deadlocks caused by functional issues are found in the post-silicon environment. This is because such a deadlock occurs only when certain conditions are precisely met. Many manufacturers still run random applicant tests over several days on hundreds of devices to find these deadlocks. And if deadlock is found during silicon test, it is not easy to analyze the root cause, and it takes a lot of time to analyze. If the deadlock is found at the post-silicon level, if you are lucky, you can avoid the deadlock through software workaround, but it usually has side effects such as performance degradation or functional deletions. For this reason, many semiconductor manufacturers and EDA vendors have been researching methods to perform deadlock verification at the pre-silicon level. Nevertheless, deadlock verification at the pre-silicon level still faces difficulties. The reason is, deadlock cases occur only when certain conditions are met. However, it is very difficult to reproduce the combination of this specific condition in the actual CPU operating environment. This is because condition reproduction using VIP or signal forcing cannot be used because the possibility of actual occurrence of the condition is not guaranteed. Even if the simulation accelerate environment is hundreds of times faster than the simulator, it is difficult to perform a random application for a long time like in the post-silicon level. We need different deadlock verification methodologies that utilizes the advantage of pre-silicon level only. In the pre-silicon environment, you can check the status of internal RT signal and use them for verifications. In other words, in a pre-silicon environment, we can create the condition ourselves rather than waiting for deadlock condition to occur with a random test. Deadlock verification in pre-silicon requires an approach from this point of view. However, it is not easy to generate these hardware events at a desired time using a real CPU operating through software. The purpose of this presentation is to show how we can freely generate desired hardware event at the simulation level. We created an action sequence model to simultaneously or sequentially generate hardware events of different actions of PSS. As shown in the figure below, even if 3 CPUs execute different actions at the same time, the hardware event for the corresponding function occurs at different time due to the state of the CPU internal cache and the processing time of the target IP. As shown in the figure below, we added delay in front of functions A and C to simultaneously generate the hardware event of function A, B, and C. But still the problem remained. The delay we commonly use in software is a method using loop delay and NOP instruction as shown in the figure. However, this software delay can only cause delay in microsecond unit and it changes depending on the CPU state. So, it is inappropriate to use it for precise hardware event synchronizations. For the sequence control of the hardware event we are targeting, it must be possible to generate a linear delay with the accuracy of clock cycle level. To do this, we added UVM delay task to test bench as shown in the figure. To link CPU software and delay counter, a mailbox interface was created between C code and system value code. And the UVM delay task checked the mailbox every clock cycle. When a delay request arrives at the mailbox from the CPU, the UVM delay counter counts the clock as many as the requested clock cycle and generate an interrupt to the CPU to notify the completion of the delay. After that, it takes several tens of microseconds to process the interrupt service routine. But this is fixed delay value, so we were able to secure delay logic with configurable clock cycle accuracy. As will be explained later, the delay with the linearity in our sequence model is very important in applying the machine learning algorithm. As shown in the figure, the test code running on the CPU is made through the PSS tools. If you set the sequence configuration for action A and action B before creating a test, An action called PSS delay is created before action A and action B as shown in the figure. PSS delay receives the delay value as input when generating the test, and this is transmitted to the delay counter of the test bench through the mailbox, and the sequence of each target action is adjusted by generating a delay as much as the desired clock cycle. Later, we will find the value of delay X and Y that can cause action A and action B to occur simultaneously by changing the delay value. To do this, many tests have to be created, and I was able to easily complete all the tasks just by setting the configuration table using the PSS tool. Another addition to the test bench along with the delay counter is the output monitor and output repository. The output monitor checks whether the target condition for each action has occurred. Target condition is described in a separate target out file and applied as an argument of simulation command. If the target condition occurs, the output monitor prints the test information, timestamp information, and action information that caused the target condition as a simulation log message. After the simulation is completed, the log analyzer extracts the output monitor message from each simulation log and store it in the output repository. The information collected here is used as training data for machine learning flow, which will be described later. The final structure of our PSS action sequence model is as follows. Now all that's left to do is to find the value of delay X and Y that have the same timestamp value. Until now, we had to observe the change result of simulation timestamp by continuously changing the delay input value to find the proper output. We solved this complex and time-consuming task easily using machine learning algorithm. From here, we will explain how to find the delay value X and Y to have same simulation timestamp value using the machine learning algorithm. Machine learning is usually performed through 5 steps as shown in the figure. Learning data is collected through setup and gathering stages, and the regularity of collected learning data is found in the learning stage. And in the analysis stage, it verifies whether the predicted result is correct through learning, and if it is wrong, the learning is repeated with new data. I will explain the setup and gathering stage. In the setup stages, settings related to test generation of PSS for data gathering are mainly made. Select the PSS scenario and select the target action to perform sequence control, and set the range of PSS delay values that the generated test will have. In the gathering stage, a test is created using the PSS tool and the simulation is executed. Then it analyzes the results and stores the learning data to be used for machine learning in the output repositories. In the learning stage, machine learning engine analyzes the results stored in the output repository to determine how the delay increase affects the output condition occurrence time. As shown in the table below, the input delay and the simulation timestamp value where the target condition occurred can be expressed in the form of coordinates. And a linear equation for each action can be obtained using the gathered coordinates as shown below. Through this linear equation, it is possible to predict the simulation timestamp value for the input delay value. In order to guarantee this linearity, we try to guarantee the linearity of delay counter as much as possible. Through the learning stage, we obtain a linear equation of 2x1 plus 1 for action A and 3x2 plus 2 for action B for common y. And as in the graph below, we need to find the positive integer value x1 and x2 that have a common timestamp value y. There is also a way to find the same y value by incrementing x1 and x2 by 1, but we applied a different mathematical approach. The linear equation for action A and action B obtained in the learning stage can be substituted with the linear Diophantine equation as follows. And by using the extended Euclidean algorithm, numerous combinations of x1 and x2 with the same simulation timestamp value y can be obtained as follows. For a detailed explanation of this process and the source code implemented in Python, please refer to the paper. We already announced the PCIe deadlock verification using PSS tool at DVCon in 2019. This time, we will show how to reproduce PCI deadlock condition with the PSS action sequence model using machine learning. As shown in the figure, PCI deadlock occurs due to conflict between ACE protocol and PCI interface protocol when condition 1, condition 2, and condition 3 occurred at the same time. Of course, please note that recent coherent bus interconnector are designed so that such protocol conflicts do not occur. The target condition that must occur at the same time to generate PCI deadlocks are as follows. 3 actions were created to reproduce each conditions, and the PSS delay action was added for sequence control of each actions. Target condition of each action as follows to detect the target condition in the output monitor. Through the following conditions, the output monitor detects the PCI RC buffer full state and the occurrence of write-back transaction and snoop transactions. The figure below shows the data stored in the actual output repository. We created a test with delay value from 0 to 100 through the PSS tool and were able to obtain the following learning data from the simulation results. The table below shows the coordinates of each delay input value and the simulation timestamp value stored in the output repository. The part to pay attention to is the item marked in red among the coordinates of action 1. This is the result that the simulation timestamp value is different from expected and the linearity is broken. This is a situation that can occur sufficiently depending on IP operation and the system conditions. In the linear regression algorithm of machine learning we used, if the linearity of some learning data is damaged, it is judged as an error compared with the linearity of other coordinates and excluded from the learning data. The linear equation of each action obtained through this process is shown in the bottom row. In order to find the solution that allows the linear equation with three different variables to find the same result, we first found the general solution for the equation of action 2 and action 3 using the extended Euclidean algorithm. Using this, we searched whether the common timestamp of action 2 and action 3 is in timestamp measurement value of action 1. Through this process, we could predict that 3 actions occur simultaneously when PSS delay action 1 is 1 and the PSS delay action 2 is 311,101 and the PSS delay action 3 207,400. Now let's wrap up the presentations. In general, one of the most difficult aspects of machine learning is collecting data for learning. PSS can generate learning data for machine learning easily and simply, just as we created tests with different delay values only by setting the configuration table. And the PSS was able to create complex target conditions using machine learning that were difficult to reproduce. I'm sure that the PSS solution combined with the machine learning techniques will be an innovative methodology that can dramatically expand our verification coverage. I still believe that the biggest advantage of PSS is that it allows you to do things that you couldn't do before, rather than speed up your existing tasks. So far, for deadlock detection in earlier stages, we have focused on increasing the speed of simulation so that random tests used in post-silicon validation can be quickly performed in pre-silicon environments. However, we confirmed that the complex deadlock conditions can be sufficiently reproduced using the PSS action sequence modeling technique using machine learning, even in the simulation environment. However, there are still areas for improvement. For deadlock verification in pre-silicons, it must be possible to predict the least expected conditions. For this, it is necessary to apply the same process as risk assessment defined in ISO 26262, an automotive functional safety standard, to the general DV process. Thank you for attending and listening to my presentations. If you have any questions, please feel free to contact me. Thank you.
Okay, so we have about 5 minutes for questions. So you can type your question in the chat and then Moonki will answer. Okay. Any question for Moonki? So Moonki, I do have a question.
Yeah.
There's actually a question on the chat, so let you answer that question first. So the question from Prabhat is, what is this process used for? Is this process used for only reproducing silicon bugs?
So this is a little different of finding bugs on silicon levels. So based on silicon levels, normally using the huge amount of randomized tests on the hundreds of silicon bases, but on our design verification levels, we have to target the specific conditions. So my paper is targeted for if we already recognize the risk for then make some bug. So our target is verify it on the simulation level. So normally we are refer the error note that has been released with CPU or interconnectors that describe the critical bug cases described on the error note. So there is a little difference. Can we move to another one?
Yeah. So the next question is, how big was the system under test, and how long was each simulation runtime?
So we are using the simulation in progress. So, but we are using the PCI environment. There is about simulation runtime has been about 3 days to reproduce like this case study, the simulations. But our targeted model for PSS on simulation is a very simple one, and our target is minimize the test because simulation is very slower than the acceleration emulation environment and or silicon. So our goal is simple and minimize the multiple tests running parallelly on simulations. So I think it is the best way to running on simulation on PSS.
Okay. And the next question, Moonki, is what was the ML tools that you use for your project?
Yeah, we did not using any TensorFlow, and we are using the Python library import. And as you see, our implemented machine learning algorithm is very basic, the linear regression algorithm, and the mathematical algorithm also we are using from the Python library. And I think TensorFlow implementations will be more high level, the machine learning algorithms, if you can utilize it. But simply, our purpose is we can use the basic machine learning algorithm like a linear regression, like something one, using the simple Python library.
Okay. And the next question is, did you use an algorithm or regression model to map inputs to targets?
So there is a regression model to map. In my understanding, it seems like a question about target conditions, how to make a target condition for our regressions. But as I said on the end of my presentations, so regression target of or the target condition conclusion is very difficult, and my proposal was for we have to some kind of flow for risk assessment like ISO 22622 to make the assessment to expect the risk on our SOC design.
Okay, and the other question is, how is your functional coverage resolved from using ML?
So actually, this my paper is not on the implemented on our real project, and our experimental result I've announced with the DVCon, and our functional coverage is result if we make some coverage bin for our the machine learning sequence model, we can expand the coverage bin because like this sequence modeling can make our functional coverage more more wide than before. That was not possible on the simulation level.
Okay. Okay. Yeah, I think we're running out of time now. So if you have any more questions for Moonki, you can contact him by email or by the. I guess you can get into the gather section and discuss more with Moonki.
Okay, so thanks for listening my poor English and last our session chair has been teaching me about many things for PSS, but he did not teach me the English. Sorry.
All right. Thanks, Moonki.
Okay, thank you.
Vinit, are you here? Vinit? Okay, the next paper is about. Oh, okay, good. Yeah. You might want to turn on your camera so that people can see you. Yeah. So the next paper is to be presented by Vinit Shenoy, and the topic is about the PSS hardware-software interface. So so Vinit is currently a validation engineer at Intel, focusing on power and performance of Intel products. He has worked extensively on pre and post-silicon platform and has over 12 years of industry experience. He has been an early adopter of the portable stimulus standard, and he enjoys exploring new methodologies. Okay, you can start the presentation now.
Good morning, everyone. I hope everyone is staying safe and doing great. So the topic I'll be talking on today is portable stimulus standards, hardware software interface to validate 4G 5G forward error correction encoder decoder IP in emulation and silicon. So what we will focus is on what HSI brings to the table, how we implement HSI in our PSS flow, and finally why HSI makes PSS actually portable. So wherever you stand on the verification spectrum from pre-silicon to post-silicon, from IP level to SoC level, I'm sure this paper will have some useful takeaways for everyone. A little bit about myself. So my name is Vinit Shenoy. I'm a validation engineer at Intel, and one of my job responsibilities is to develop PSS models for Intel's internal IPs, and along with looking at power and performance for Intel products. Okay, so let's get right into it. So let's have a look at the problem statement. So if we look at the different platforms on which test cases are usually run, you have, let's say, a virtual platform. You could run it on simulation, emulation, FPGA boards, and silicon boards. Whereas the test case itself, you could run it, let's say, at an IP level. You could have a subsystem level environment or an SoC level environment. Now, if you make a broad generalization, UVM is pretty much the methodology of choice when it comes to pre-silicon simulations. And when you have embedded cores, so you would either run, let's say, bare metal C test cases, or you could have some OS content. Now, while UVM is great with its constraint randomization, you cannot run UVM code on, let's say, an embedded core. And similarly, you cannot use your OS content to drive a UVM agent. So this pretty much creates a portability wall where you cannot have content developed for one platform running on another and vice versa. So the development of PSS was expected to break down this wall and sort of merge these two diverse worlds. But if you see the current PSS world without HSI, the PSS solver will handle your configuration space, it will handle memory allocation, it will do your scheduling very well, but it actually doesn't help you much with reuse across platforms, and it doesn't really help you with driver development. So, so the PSS users would usually work around this limitation by using certain tricks. I would call them tricks, which would mainly involve around having a separate set of exec bodies for each target platform. So let's say you plan to run your content on UVM and then on embedded cores. then you might use one of these two approaches. So the first approach would be to have two separate exec bodies, one for UVM and one for your embedded code. And in the UVM exec body, you basically generate your UVM sequence with your PSS tool. And similarly with the embedded exec body, you generate your C driver. The second approach is pretty much similar, where you have one single C function call in your exec body. That is a single exec body for both your UVM and your embedded tests. But the C exec body basically calls a C function, and the C function would either call a UVM task via DPI calls or a C driver function. Uh, and here both the UVM task and the C driver have the same name and parameter definitions. So with either of these methods, you would still require to develop both your underlying UVM sequences and your C driver code. So this is basically a duplication of effort, and this is where HSI comes in to save the day with a single implementation of your driver code. So all in all, so what does HSI bring to the table? So first off, it abstracts the mechanics, the lower level mechanics of your register accesses, but it does much more than simple register abstraction. It provides a representation of, let's say, of memory, of interrupts, synchronization directives, messaging, and basically it gives you a very efficient way to implement a portable driver logic. So your HSI sequences can be mapped to both, let's say, a UVM agent-based environment and for embedded core-based environments. So basically in future slides, we'll look at a much lower level implementation of HSI. So in this slide, we have tried to capture the HSI development flow. So the first thing we need is the PSS register models for all the IP blocks which we plan to use. So for this, you need to have some sort of register automation which will convert your register description format into PSS register models. So a lot of EDA tools now have out of the box flows where, let's say, they convert IP exact into PSS register models. At Intel, we have a custom XML format for register description. So we had to develop our own register automation scripts which took this XML and converted it into PSS register models. Now these PSS register files become the basic building blocks for your HSI sequences, and these sequences basically become part of your PSS model in the exec body, and then this is consumed by your PSS tool of choice to generate scenarios, and eventually generate code for the target platform on which you plan to run your test case on. Now let us have a look at how a register file looks like. So here we have a basic register struct defined under the reg group C component, which is the base type for specifying register groups. The register itself is defined as a packed struct. The register is then instantiated over here uh, using the parameterized component reg underscore C, and this is the offset of the register within the register file. So the base address of the entire register file is provided when the component is instantiated, and we have a more detailed code snippet of register component instantiation in the full paper which will be published. Now the reg.c component provides four functions: read, read val, write, and write val, which may be called from the test realization layer of the PSS model, which is basically your exec body. Now here we have a simple PSS action which shows a simple register write using HSI. So here we have an instance of the register struct, and we update the field with the randomized value in post solve. Now in the exec body, we are basically using the HSI write function and passing the instance of the register. Now instead of write, you can also use write val function if you want to write to the entire register. And in this case, you can, let's say, pass a 32-bit value instead of the struct instance. Now that we have the exec body nailed down, now comes the most important part, target code implementation. So how does this write function look in my generated code? So when we talk about target code implementation of HSI sequences, it is important to point out that PSS standard does not impose specific rules on target code implementation. So PSS tools are free to implement their own way of generating the target implementation code. So if the target platform here is an embedded core environment, the target code might look like a simple pointer based access to the register. Now, if the target platform is UVM, then there will be some additional integration required to drive the transaction for the register write on the UVM agent. So in our paper, we have provided more code snippets on how HSI to UVM integration looks like for the EDA tool which we have used. And finally, HSI is not just about writing a register. You can write an interrupt handler. You can poll on a condition. You can add synchronization points between, let's say, concurrently running driver code. You can combine it with PSS memory allocation to, let's say, write the address handle of a descriptor into an IP register. So you have things like for each, you have repeat, you have if statements which can be used to, let's say, generate conditional code. You have write struct function which can be used to write a pack struct into memory, which we have used to write our DMA descriptors into memory. So with all these capabilities, you can basically write your driver code in HSI, and there is no need to write platform specific driver code like UVM sequences or C drivers. So this basically summarizes the hello world basics of writing your HSI sequence. Now that we have a basic understanding of the HSI flow under our belt, let us take a look at our design block and how we develop PSS HSI models for it. The, the IP block is basically a 4G 5G accelerator. As communications service providers move from 4G to 5G networks, many are adopting virtualized radio access networks, also called as VRAN, for higher channel capacity and easier deployment of edge-based services and applications. VRAN solutions are ideally located to deliver low latency services with the flexibility to increase or decrease capacity based on the volume of real-time traffic and demand on the network. One of the most compute intensive 4G and 5G workloads is the RAN layer 1, which is forward error correction FEC, which resolves data transmission errors over unreliable or noisy communication channels. FEC technology detects and corrects a limited number of errors in 4G or 5G data without the need for retransmission. FEC is a very common function that is not differentiated across vendor implementations, which makes it an ideal candidate to be an on-chip accelerator. And since the FEC acceleration transaction does not contain cell state information, it can be easily virtualized, enabling pooling benefits and easy cell migration. So you can see from the block diagram that there are multiple instances of these 4G and 5G FEC blocks. Uh, so there is a 5G FEC decoder, which is basically used during 5G downlink. Similarly, there is 5G FEC encoder, which is used when you are transmitting 5G data, and similarly for 4G encoder and decoder, which is basically 4G uplink and downlink. And you also have a DMA block in the IP, which is used to transfer data from DDR to the IP blocks. So the data flow is pretty simple. The CPU receives data over the radio network and it writes this data into memory. The CPU then writes a descriptor into memory which contains addresses of input data blocks and addresses of blocks for output data. The descriptor address is then written into queues which is present within the IP. and the DMA engines present in the IP fetch the input data, and they also write the output data back into the memory once the FEC blocks are done processing data. So how does HSI fit into this picture? So as you can see, we have multiple instances of these 4G decoder, 5G decoder. So basically, this is multiple instances of the same register file. So when we are instantiating the register component, we are basically instantiating it as an array depending on number of instances of the component. So even over here, so let's say for 4G downlink, we have instantiated the register component number of 4G FEC DL times, which is a constant. Similarly, for the PCI virtual functions, we have instantiated the VF register array number of VF times, which is 16 in our case. So we have 16 virtual functions. Now the base addresses for each of these instance is also saved within a configuration table. So let's say in our example we have 3 instances of 4G downlink, and the base address of each of the register array is saved over here in a configuration table. So this makes your PSS model very scalable as well. So in case you have multiple SKUs of the silicon, and each SKU might have a different combination of instances of these 4G 5G blocks, then it is very easy to modify your PSS code and this configuration table to match for a particular SKU. And again, this is where the PSS randomization works very well with your eventual HSI sequence. So let's say I want to write, I have randomized a 4G downlink scenario, and I have randomly picked up instance number 2 for the transfer. Then the exec body can automatically write into the instance 2 of this register component and then the associated register within that component. Uh, so this is how we have basically used the randomization of perspec along with the HSI sequences we have written to develop our portable driver. So finally, I would like to summarize all the HSI features which we have used and show some results of our experience on using HSI. So on the features which we have used, the first one is register file instantiation and address factorization, which pretty much points to the table which I showed in the previous slide. Uh, Another interesting one was handling non-contiguous register arrays. So in our IP, we had a lot of registers which are basically register arrays. So if we see over here, this is a register which is basically an array, and so if you assume it to be a 32-bit register, you would assume that all the registers are at an offset of 4. But here the registers were at a non-contiguous offsets. But HSI gives you a way to set the offset as well. So while initializing the register, you can just have a for each loop and then have your own formula of how much the offset is for each register. Similarly, we did something like so combining PSS randomization with HSI sequences. Uh, so we had a line like this in our exec body. So where VFID and QID is something which is randomized by your PSS tool, and based on these randomized values, the eventual register to which your data will be written to is populated. So here VF is from the 16 virtual functions. It basically picks one of those virtual functions which got randomized, and within that register array, then it writes to, let's say, the queue manager ingress AQ register to the randomized value of queue ID. Another thing which we tried out was incorporating the ISRs into HSI. So HSI has two functions. So basically you have a PS event which can be used to model events, and you have a wait and an emit function. So more details on uh, the actual code is present in the paper which will be published. Uh, so interesting thing on ISR is we wrote the ISR. You can write the ISR even at the UVM level. So let's say you have an IP level environment where you do not have an interrupt handler. You can still have your test bench, which is basically monitoring the interrupt signal, and whenever the interrupt is raised via CDPI callbacks, you can actually call your uh, ISR, which is written in the C code. And then on SOC level environment, where you have the embedded cores, you anyway you program your interrupt controller as well, and then you have the standard way of servicing ISRs. But the ISR handler which you write, so that basically doesn't change whether you are on a UVM level or on an embedded core. Only the integration around it slightly changes. Uh, Another point which we really liked is HSI and efficient target code generation. So with HSI, so you have if conditions, and you can generate a lot of conditional code. Uh, so let's say there is a feature X in the IP, and if X is enabled, you have to write some 5 registers, and if that feature is not enabled, then those registers need not be programmed. Uh, so this might be a feature of our PSS tool as well, but basically uh, if an if condition is not satisfied, you don't generate that code in your target implementation. Uh, so your generated code is very concise and crisp, and it points to the exact code which is going to drive your traffic. So there is no extra fat uh, in your generated test code. And so the thing with HSI is HSI blurs the distinction between your driver code and your test code. So typically you would have, let's say you would have a UVM sequences, and then you would have a UVM test, let's say, which calls these sequences. Or in C world, you basically write a driver, and then you have a test case which basically calls these driver functions, and then that's how you have a test case. But with HSI, the distinction is pretty much blurred. So it's basically a single file which is the driver and the test case in a way. Uh, so the advantage of that is every test case is self-contained. Uh, you don't depend on an external driver file. So uh, you compare this with, let's say, a C world where you have a driver and a test case, and the driver keeps getting modified. So let's say if you have a 2-month-old test case, and the driver has changed so much, so that old test case now stops working. But this won't happen with this HSI flow. Uh, so challenges, we did see some issues, and most of those were around address handling, and some were around some tool specific issues which eventually got fixed. With respect to address handling, so we had a scenario where we have a register, and in the register I have to write only the upper bits of some address, allocated address, and then the lower bits are some randomized configuration parameters. So we found this difficult to do with HSI, how to take a bit slice of an address and then merge it with some parameters and then write it into a register. So here we use some non-PSS ways to do it. So overall, yeah, we did see a reduction in test development time by close to 70%. We did get a good reuse across platforms. So we started this on emulation and ran this on post-silicon because I'm from the emulation team, but the plan is for the next project, even the pre-silicon guys use basically the same model. We could achieve good IP coverage checkout and uh, develop concurrency stress scenarios, and the test case in itself is quite scalable. At a long term, the big benefit we see with HSI is, I would say, you can use the best target uh, platform for the best task. So what I mean by this is, so you can basically develop your HSI code in, let's say, an IP level UVM environment where, let's say, the runtime would be small, so that by the time you reach emulation, you can run much longer test cases, complicated test cases, and you don't have to waste cycles developing test code. So this is something we face a lot in emulation, as emulation slots are pretty expensive, and we usually do end up spending a lot of time when we are developing a driver from scratch on emulation. So that has some advantages of HSI. Uh, so this is all I had to share. I think I am just in time, so open for questions. Thank you, everyone.
Okay. So you can unmute yourself and ask the question to Vinit directly, probably faster than typing.
Yeah, so okay, so one question I see is ISR, I guess it is PSS 2.0, although I am not exactly sure. For me, it's just the tool version which I used. And I think to come on the question where is the IP team seeing any benefits? We could generate a lot of scenarios which IP level team could not generate with UVM. And they were more specific to either configuring the IP or address handling. And the post silicon, obviously, I think the main takeaway was we saved a lot of development time before silicon arrived, and coverage is something which post silicon world does not usually have any methodology around.
Okay. Any other question for Vinit? So with respect to the ISR, I got the answer from Swami here. It's in PSS 2.0, and PS event are coming in PSS 2.1. Any other question for Vinit? You can, I think everybody can unmute themselves, but if not, you can type the question in the chat. Okay. If
No
there's
questions.
no
It's either good news or bad news. So.
Well, that's because you already answered the questions during the presentation, Vinit, so you answered quite a few there. All right, I guess we can start the next paper. Thank you, Vinit.
Thank you very much.
So the next paper is will be presented by Matthew Ballance. The topic is code developing IP and SoC bring up firmware with PSS. And Matthew works as a functional verification product engineer at Siemens EDA with focus on stimulus generation techniques and the Accelera PSS language. He has a lot of experience in the areas of hardware-software co-verification, virtual prototyping, and IP encapsulation. Okay, yeah, you can start the presentation.
Hello, I'm Matthew Ballance with Siemens EDA, and I'm here to present my paper, Co-Developing IP and SoC Bring-Up Firmware with Portable Stimulus. Just a recap of our basic IP and SoC verification flow. At the IP level, we typically verify our IPs using a UVM test bench written in System Verilog. In this environment, we have a UVM register model to use in writing and reading the registers within our IP, and we can write directed and constrained random UVM sequences to exercise behavior in the IP. And this is quite a productive and efficient way to create tests. Once we have assured correct functionality in the IP, we hand off the design RTL to the SoC team, where the RTL is integrated into a larger SoC level design. In an SoC environment, tests are carried out in quite a different way. In this environment, we need to write embedded software tests that run on the processors in the design, and these embedded software tests are what access the registers in the IPs, program them into different modes, and test the integration of all the IPs in the SoC environment. Now, creating these bare metal embedded software tests is actually quite a challenging proposition. In today's complex SoCs, there are lots and lots of cases to exercise, and with bare metal C tests, we typically only have directed testing techniques for test creation. Moreover, we need to use all the processors in the design because they are, after all, part of the design. We need to run them and deal with the concurrency and parallelism with these to truly exercise the design's behavior. Now, Accelera has standardized a new language, Portable Stimulus, or PSS, and this allows us to bring in some of the constrained random testing techniques and bring that we're familiar with from the System Verilog environment and bring that up to the SoC level. PSS allows us to model our scenarios in terms of more abstract things, actions that represent behavior, resources that the actions need to have in order to exercise behavior, and data flow between those actions. Because these scenarios are constrained and randomized, we can create multiple tests just like we do in System Verilog by changing the seed and creating new test variants. And we can use constraints, much as we do on UVM sequences, to focus the behavior of these tests. And again, get a productivity boost in creating more tests more quickly. Now, in looking at PSS, it's important to realize that there really are two key parts to a PSS model. There is the part that describes the test intent. What is it that we're testing? What's the high-level picture? This is where we have actions that capture the big picture for behavior and resources and data flow that really capture the rules around how those actions can relate. What's very critical, of course, is that we have to somehow relate this high-level abstract model down to the lower-level details of how do registers get programmed in the IPs, how do we interact with interrupts, all the lower-level detail that actually makes a test go at the end of the day. So the high-level modeling details of PSS really help us describe tests much more quickly, but it's critical that we have the lower-level test realization, which is like driver software in place to make the tests actually connect into the design. So looking at PSS in the context of an IP development and SoC verification flow, it makes sense to talk about expanding somewhat what is delivered along with an IP. Not only do we want to hand off RTL to the SoC team, we want to provide the beginnings of test content to the SoC team. Now, in the context of PSS, this means handing off some reusable pieces of PSS code that they can assemble into a larger scenario, but it also means handing off some low-level driver code, some low-level firmware to connect that PSS to the design's registers. And in this paper, we'll look at a technique, a flow for making that happen. So from a mechanics perspective, it would seem that adding software or firmware into a simulation is a pretty simple proposition. System Verilog has the direct procedural interface, DPI, that allows System Verilog to call C code and C code to call System Verilog. And there have been quite a few examples that I've seen, that I've read papers on, of compiling C code, wrapping it up in DPI, and integrating that with a UVM simulation, either as a way to get a reference model included or perhaps include some simple firmware. But just doing this, just including a little blob of C code in our System Verilog UVM environment, certainly doesn't get us firmware that we can readily share with the SOC team and that they can readily make use of. So what are the challenges? Well, the big problem is that when you get to SOC level, you don't just have one little blob of C code. You have lots and lots of little blobs of C code that represent the firmware for each of the IPs in the design. And unlike at IP level, you don't just have one IP instance, for example. You might have multiple instances, much as we have two DMA engines in this SOC. And the little blobs of firmware need to be properly configured to know what the proper base address is, to deal with the fact that there might be multiple instances of an IP. So this firmware really needs to be able to coexist. The firmware that we develop for our IP needs to be able to coexist with the firmware developed for many other IPs. So we need some sort of an interoperability framework, and we could go off and design one, but it's always good to try and avoid that, especially if there's something else in the industry that we could make use of. So you know who else has this problem, as it turns out? It's people that create operating systems. When you think about Linux, when you think about Windows, these operating systems, of course, need to manage multiple drivers as well. And multiple authors need to be able to create a device driver that interoperate and cooperate with drivers from many other authors. We have the same configuration challenges in terms of specifying the base addresses, so on and so forth. Of course, the only challenge is for us in verification, using a full operating system like Linux or Windows is far too heavyweight for us to make use of in simulation and emulation verification. The startup process is very long. It takes a lot of memory. Frankly, if we did this even in emulation, we would spend most of our runtime waiting for the OS to boot before we ran a little bit of test code. The good news is that not only are there operating systems, there are real-time operating systems, or RTOSs. And RTOS has many of the same requirements around device drivers that an OS does. Manage multiple types, manage multiple instances, deal with all of the configuration challenges. But an RTOS typically is designed to work on very low power, very resource constrained systems. So in this paper, we look at the Zephyr RTOS, which is an open source RTOS maintained by a consortium of, frankly, volunteers, as well as some companies in the industry. It's really targeted at IoT, Internet of Things type applications, which are very small footprint for memory, often very low power. So the Zephyr OS is a little bit different than what you might think of as an OS. If you think about Linux, if you think about Windows, you think about booting up the OS, you think about loading an application on top, and you run that application. And application and OS are quite separate. Zephyr and several other RTOSs change that model a little bit. Because of their target, the OS is a little bit more like a library. When you compile everything together, you compile your test or your application right along with the operating system, and it results in a single image, a single executable that contains both the operating system and the application. Now, for testing purposes, this is actually great because we don't have to deal with some of the complexity of, having a file system for the software running for our test, and it's a lot simpler. We don't have, there's less complexity we have to deal with. The Zephyr OS is also very tiny. You can configure it in a typical test configuration such that the memory footprint's around 8 kilobytes, which is very doable for a verification environment. So frankly, the Zephyr OS and many others are substantially close to a bare metal software environment, but we get some of the same benefits of having a driver framework to make our drivers interoperable. So let's talk about how we might integrate a Zephyr type environment with our IP UVM verification environment. So first off, it is C code, so we can compile it, but recognize that it creates an executable, so we can't necessarily load it in via DPI. We could cross-compile this to the processor architecture that we believe we'll be targeting eventually, but this has its challenges as well, and it doesn't really bring us that much benefit. So the good news here is that the Zephyr RTOS is able to compile everything to a host executable. The typical application of that is for Zephyr application developers, where they can, host compile their code and use their traditional debuggers and other tools, but run that against the APIs that the RTOS provides. But it's not too hard to repurpose this to do co-simulation of the software behavior with a UVM environment. And the paper goes into a bit more detail on how this is done. There's a bit of a framework, some open source components, including a UVM agent that connects up to the register model to use the register model as a way to access the device registers, and then also provides services for channeling interrupts back up to the software behavior represented by the Zephyr executable. Okay, so touching briefly on the process of creating a driver, and again, the paper goes into a bit more detail here. The Zephyr RTOS specifies a format for drivers in the system. It specifies the data types you have to use and the data structures you have to define, and how those fit into the driver framework such that you're able to configure the various aspects of the driver. Zephyr defines several standard APIs for standard devices like DMAs or serial devices or timers, but you can of course use custom APIs as well if you have devices, which is pretty common, that are quite custom. Now, I think the significant thing to look at from a task of driver creation here is that the operations that we're performing here, writing registers, reading registers, having behavior that's triggered when an interrupt fires to manage the device, these are all things that as UVM sequence writers we're very familiar with. It's the same task to write in system Verilog using the UVM register model. It's the same knowledge and the same information required to create this driver C code. And I'd argue that does mean it makes a lot of sense to have the IP level design and verification engineers also create this, because it takes advantage, it leverages the knowledge that they need to have to create a good UVM test bench in service of creating some low-level driver firmware. Okay, so we've talked about some of the infrastructure that allows us to build up that test realization level. But now let's talk about PSS again. So even at the IP level, even when only dealing with a single IP, writing bare metal C tests is not an easy task. So as the paper talks about, we'll look at segmenting our PSS model into two pieces. One piece that we will use at IP level, but will also be useful to the SoC team, and then some scenarios that we'll use primarily at IP level. They won't be reused directly by the SOC team. Now, it's important, I think, to note here that when we're talking about PSS working together in this process of creating a low-level driver firmware, we're not replacing the UVM as a verification flow. We're still relying on the constrained random coverage-driven UVM flow to verify the functional correctness of the design. We're creating the PSS content here initially primarily as a way to verify the low-level driver firmware and the reusable PSS elements that we'll hand off to the SOC team. We can create some more involved scenarios with PSS at the IP level, but that's not really the primary point here. Okay, so let's talk about the building blocks. This is the part that's reusable that the SOC team can easily reuse. So what we're essentially doing here is defining an interface to the low-level driver code in a much more abstract, much easier to reuse form. So this is some PSS code on the right-hand side here, where we're describing a component, which is what PSS uses to represent a physical IP block. In this case, it's a DMA block, and so we need to capture some rules around the resources that this block has, the DMA channels, and the fact that only one behavior can use a DMA channel at a given time. Down here at the bottom, we have an action for doing a memory-to-memory transfer on a DMA channel, and this contains all of the constraints that dictate what a legal channel is or what a legal transfer is, and spell out the resources that a transfer requires. And here at the bottom, we have a call out to that low-level driver code, a function in that low-level driver that actually will cause the DMA registers to be programmed. So we'll be able to use this at the IP level for creating scenarios. We'll also hand this off to the SOC team, which will allow them to create scenarios more efficiently. Okay, so when we hand things off to the SOC team, in addition to the RTL, we're going to hand off that low-level driver code, which is integrated. As you saw, it's connected to the PSS scenarios or the PSS base level actions. All of this gets connected together with all the other IP firmware into an SOC level software image. And Zephyr uses what's called the device tree. This is used by Linux as well, to capture the details of what IPs exist, what the register location is for the various devices, and to configure things like where do interrupts, how are they hooked up. Here you can see, for example, that the base address of this first instance of the DMA is a hex 8, and the second is hex 8100. The Zephyr RTOS then connects this information and properly configures instances of the device driver. And as I mentioned, part of the goal here by handing off PSS code supported by low-level firmware is that the SOC team can very quickly and easily set up scenarios by using those lower-level actions. And because those lower-level actions are connected to device firmware that are properly configured by the Zephyr RTOS, it makes it very easy to very quickly create some scenarios and then iterate and create even more complex scenarios. So in this paper, we've taken a look at the task of IP and SOC verification and how we can enable tests at the SOC level to be created much more efficiently using PSS. And a key requirement of that is that we have lower level driver firmware available to be used by the PSS actions. We've looked at the Zephyr real-time operating system as a way to enable multiple firmware modules, drivers to integrate together and to cooperate and not stomp on each other. And we've seen how we can write reusable PSS elements on top of those drivers such that the SoC team can very easily and quickly create scenarios once we get to the SoC level. So we've seen also how we can connect Zephyr as an RTOS with software running on top of it into an IP level environment that lets us test out the firmware and verify that using familiar host-based tools. So thank you very much for taking the time to attend this paper. You can certainly find more details with more code samples in the paper itself. And I'd encourage you to take a look at Zephyr and potentially other real-time operating systems as a way to create firmware earlier in the verification process, leverage the knowledge and expertise of the verification engineers and design engineers to create that firmware more efficiently, and then use that along with the RTOS as a framework to deliver that along with the IP to the SoC team. Thank you very much, and I think we have a few minutes for questions now.
Okay, we're actually doing pretty good. We have about 8 minutes for a question. So just a reminder, if you prefer, you can unmute yourself and ask the question directly. But we do have 2 questions in the chat, so let Matthew answer those 2 questions first, and then you can ask additional question.
Perfect. Thanks, Vu.
Okay. So the first question, Matthew, is from Ferris, is whether it's fair to say that this is only applicable to driver code that can or has to be compliant with Zephyr's required driver framework or writing style. And then if one has firmware with its unique C API specification, how could this be made useful? Another layer on top of Zephyr?
Right. No, this is a good question. The paper does assume that the base real-time operating system or environment is Zephyr, and makes use of the infrastructure that Zephyr provides for driver aggregation and configuration, and leverages some of those along with PSS as well to aid in PSS content creation. So in a sense, yes, the assumption is that you're using that framework and the conventions. If you have existing C code, let's say it's not necessarily tied to an existing firmware framework, it's not too difficult in general to wrap that up as a Zephyr driver. The framework's pretty lightweight in keeping with the character of the real-time operating system overall. If you have your own firmware framework, I might look at this paper more as illustrating a concept more so than a specific technology. So, the concept of using a firmware framework as a way to encapsulate, blobs of firmware and ensure that they're efficiently assembled and configured along the way, and to start that process of development at the IP level. So if you have your own firmware framework, I might be looking at that to see how can you integrate that into an IP level environment effectively. Does it have the right hooks to enable PSS content creation to reflect the firmware structure? You would probably want to ensure that some of those aspects are built into your own custom firmware framework. As I mentioned in the paper, you can always roll your own. My question here was really, could something from the industry be leveraged as well?
Okay. So your next question, Matthew, is how does your firmware communicate with test bench for event scheduling? Right.
So the slides treated that topic somewhat lightly. The paper goes a little bit more in detail. So at the IP level, the Zephyr software behavior is running as an executable. It's running in a separate process, a separate program from the simulation, and it communicates via sockets back into the simulation via DPI. So there's some system Verilog code, there's a DPI stub that results in calls back into UVM that get turned into reads and writes to the UVM register model. So in this case, the software is by and large considered to be non-time consuming, or in other words, it's not necessarily registering time callbacks with the simulation. It calls out and says, I want to do a write. The simulation runs until the write is complete, and then the software behavior continues on. Similar for waiting for an interrupt, for example. If the software goes idle, the separate process will say, I'm going to wait until the UVM environment triggers an interrupt back up to the software. So it's kind of an arm's length event-based synchronization.
Okay, and another question from the same person. I can't pronounce his last name. Sorry.
No worries.
So there's can your SOC team collect functional coverage information from running your firmware test?
Now, there are a couple of ways I can look at that question. Functional coverage with respect to what is kind of the key question, I think. There's actually some interest, I've seen some interest in collecting metrics on the firmware itself, what aspects have been exercised. This paper doesn't really go into those details. That's I would consider that a separate topic. Likewise, you could think about firmware with respect to coverage with respect to the design itself. That would be handled via existing mechanisms, system Verilog cover groups, monitors. Question from Prabhat here. Any thought about using PSS as part of production firmware? That's an interesting aspect of philosophy, let's say. The previous presenter pointed out that the advantages of considering kind of blurring the line between test and firmware. So you sort of thought about this as one thing. I often think about there being benefits in maintaining some separation between those two things, given that firmware can be used by things other than the test. It's very important for tests, but it can be used by production software as well. So at the moment, this work certainly is considering there to be two layers. There's a test layer and there's a firmware layer, and they're integrated, yes, but they are distinct.
Okay. Any other question? I think we have enough time for at least one more question.
Yep.
Okay. I guess not. So well, one thing I want to remind everybody is to remember to go into the voting section of the virtual page and vote for your favorite paper. Also, you can go to the gather section, to visit the exhibitors. Okay. If no more question, thank you, Matthew, and thank you, everybody. Thank you, everyone, for attending this session.
Thank you all.
All right. Bye, everyone.
Thank you, Paul.